Hello, good morning. So this time we're going to be looking at finding formulas for linear functions. What I'm going to try to iterate throughout this lecture is that the formulas for a linear function are set up so that all the stuff is viewable from the outside. So, my joke is that you can judge a book by its cover here because all the important information for a linear function is given in the formula depending on the form it's given in. And just like in the English language, you can rewrite words like can't into cannot and they have the same meaning. We can re-represent functions' formulas in the same way. So you might see something like this, which you should recognize as y equals b plus mx form. If not, you should check out the last video. And I'm going to introduce a new form called point-slope form. Point slope, and it is exactly what it sounds like because we don't name things creatively in math. We try to be clear. Point slope form tells you a point and the slope of the line. So what I'm trying to highlight with these graphics here is that all the important information is right here. Here's the y-intercept, 0, 3 is given right here. And the slope of this line, if it was up 2 over 5, that would be given here in the formula. And there's really only two things you need to know about a linear function, and that is one point and the slope. So it works here, and then for a different line we could represent it using this is what we call point-slope form, and I'll unpack what this notation means later. But not just for the y-intercept, but for any point that it passes through and a given slope, what this would look like. So for example, this line crosses through the point 4, 2, x equals 4, y equals 2. And so you'd see these values 4, 2, and then the slope here as well, right here in the formula. So it's something that right from the cover of the book you can tell what's going on with this thing. So I hope by the end that this is kind of your takeaway and that these things seem less and less like a jumble of numbers and letters and more like a clear description of a relationship, right? And the point and slope can be just values from some random line like I have here, or they can represent a rate of change and an actual starting value or a data point that I have that mimic what's happening in the real world. So let's dive in with a few examples and we'll check this out. So again, to jot this down, that you only need two things for a line. There's only two pieces of information you really need. One is a point. It can be any point that the line passes through. So something that, looks like this and it has some coordinates. And we use these notations x1, y1, or x0, y0, or what we call x0, y0, to just represent single points instead of x and y, which typically are allowed to have varying inputs, right? So x0, y0 might be 1, 4, or it might be, 3, 7. So they're particular points. So you need to know one point, at least, and the slope. And the slope dictates how it changes, and it will get you all the other points on the line, but you need to know at least one point so you know where it starts or where to start from to generate the other points. So if you think about, just drawing a line in space, there's two things that are really interesting about it. How steep it is, right? So this one versus this one. Their steepness are different, and also where they are in space, which is dictated by a given point. So as long as you have this information, you have everything you need to know. The alternative is that you have just 2 points given, but then you still have everything you need, because if you have 2 points, 1, 2, well, what can we do to get the slope if that's an important piece of information? Well, we can just take the slope between those 2 points, y2 minus y1, the change in the rise over the change in the run. Okay, so let's have that kind of be in the backdrop of our brains as we work through a few examples of generating the formula of a linear function. Okay, so here's an example of a good linear relationship. So trash removal costs around $300 a year in this area. And then you'd be charged a fee for any non-standard pickup. So let's say for this given company, it's $40 per standard pickup. So what we're being asked to do is create a formula for an annual cost of removal as a linear function of the number of pickups. So I want to address something which is, I think a lot of students get stuck on, where do I start, with a problem like this? And so this is where we kind of jot down, what we know or what we have, and then also what we want. What are we being asked to do? What's the solution to this problem? Well, the solution to this problem is a linear function, creating a formula for a linear function, which is going to be of the form y equals b plus mx. Right? That would be a fine way to go about it. And we can even be a little bit more specific and say, well, this isn't just y and x that are related. It's cost is a function of the number of pickups. So we could say this is cost C in dollars. I usually make my variable names remind me what they are. So cost is a function of the number of pickups. We'll call this n. And that's going to be equal to some b plus m times n. All right, instead of y and x, we've got c and n. So this is really what I'm after, this linear formula, this formula for a linear function. And what are the things that I'm missing from this? Well, I'm missing b and I'm missing m. We know we want to have n and c vary. If I'm looking for a formula, that means I need these as variables, but I need b and m. So what are b and m? Well, this is my vertical asymptote, or vertical intercept. Oh my gosh, I did it again. Vertical intercept, or initial value. Right, that's usually what b means for a linear function of this form. And then m, well, this is the slope, aka the constant rate of change for the linear function. So let's see if we can go in and find these pieces of information. So trash removal costs $300 per year plus $40 for any non-standard pickups. So here, this $300 each year, this per year, this is the annual cost. This is the units of the output. And so this is we know cost equals 300 when n equals 0. Right? How do I know that? Well, if it's starting at $300 per year and then we add some extra stuff, this must be the case when there's no extra pickup, so when n equals 0. So it might take you a second to realize that, oh, well, now that I have this data point, this is exactly this value here. The vertical intercept, or the initial output value, I'm looking for the point 0b, and here it's 0, 300. Right, because here's my n equals 0, here's my c equals 300. Okay, so this is my b value, is 300. So we've got that, so we can kind of update our problem here, 300 plus b times n, and now we're on the hunt for m times n. Why did I say b there? M times n, right? Looking for this value here. So looking for the slope, the constant rate of change. So question is, well, what does this value tell me? $40 for any non-standard pickups. Well, think of the units. What are the units of this thing? It's $40 per one pickup. right? If I had 2 pickups, it'd be $80. If I had 3, it'd be $120. So this is a $40 per one pickup. This is a rate, right? It's a comparison of one unit to another. So dollars per pickups. So this is actually my slope right here. This is my constant rate of change. It's changing the output $40 per one pickup. And numerically it's just 40. So this is my constant rate of change. That's tied to this guy here. So M is 40. So then I know this whole thing, this whole formula, must be equal to 300 plus 40n. And so then we can give ourselves some room. I've got another example beneath here. Let's give ourselves some room and just say, okay, well now we've got C equals 300 plus 40n. And now I have cost as a function of the number of pickups. So if I had a really crazy year and I had 100 pickups that year, that's going to go in for n and tell me how many dollars are going to be charged for each of those, plus the 300 for the year, and that will get me my total cost, right? So this is how I would create a function given a constant rate of change and that initial value, right? That vertical intercept in b plus mx form, okay, or what we call slope intercept form. First, start off with what you want, then think about what you have, and then try to map things from what you have to what you want. And it might take some problem solving to get those things. It's not always just going to be identifying what they are, but at least you know what you have, what you want, and then this is the tricky part, right? Is either mapping it over or figuring out what you need to do that. And again, here there was a assumption made of input and output. And I didn't say this clearly at the beginning, but this is how the language lent itself by saying formula for cost as a function of pickups. We know that n would be the input and c would be the output. Okay, so then we knew that m would carry these units. The slope would carry these units of the change in cost over the change in the number of pickups, which would be dollars per pickup. Okay, so just to kind of keep this all tethered together, in case these first things weren't clear, you could go to, what else do I know? And start to draw from it as like a well of resources. So in the second example, we've stripped out the context of any physical meaning, and we're just looking at a line, which again has its own value in doing so. So let's say I know that for this function f of 0 equals 5/3, and I know y equals f of x has a constant rate of change of -2. So again, we're being asked, here to create a formula for y as a linear function of x. So the question is, what do we want? Well, we want b plus mx as the expression that gives us the y values for a given input. So what do we have? Well, we have f of 0 equals 5/3. And we can unpack what that means. We know that the constant rate of change equals -2. So that comes from here. And we know this came from here. And that's about all we know, right? That's all that's been given up here. So we've got all the information given to us. Now it's time to kind of suss out from what we've been given what this really means and how it maps over to what we want. So, we want B and we want M. We want the vertical intercept and we want the slope, or the constant rate of change. Well, I just said the magic word, right? Constant rate of change. This equals the slope. And so we know that this equals -2. So right here I already have my slope value. So I know I'm looking at B minus 2x. And so now it's really just left up to find what B is. Can I get B from this piece of information? Well, what does this really mean? This really means that at an input of 0, y equals 5/3, right? Because y equals f of x. So this right here, input of 0 gives me an output. This is my vertical intercept. It might not have been clear since it was in function notation when it was given to you, but this is actually your B value. So now we've got y equals 5/3 minus 2x. And again, what's the nice thing about y equals b plus mx form? It's got everything you need right here, the point and the slope. So if I wanted to graph, we've solved the problem and we're good to go. But if I wanted a different perspective, go to a graph, I would know that this graph starts at 5/3, so here's 1, 2, 3. So 2/3 of the way between 1 and 2. And then it has a slope of -2, which is really -2 over 1, right? If we're talking about rise over run. So it goes down 2, 1, 2, over 1, and looks something like this. Oops. All right, down 2 over 1, that's my M, and I knew that this value right here is 0, 5/3. So I know everything there is to know about this line, and it's represented right here in the formula. And that's true for every line as long as you can write it like this. So what I'm going to show you now is another helpful way to represent lines called point-slope form. We're going to first show you where it comes from first. You're not going to be tested on deriving this or even being able to recall where this comes from necessarily, but it does help to understand that this isn't just magical formula that I'm giving you. It comes from things that we already understand. So this requires that you remember that the slope formula between any 2 points is the change in y over the change in x. We measure change with a difference, so it's the end minus start of the y coordinates and the x coordinates. And so what we're doing here is saying, well, the slope is going to be constant on any linear function, right? So instead of fixing this x2, y2 point, let's say I wanted to do this in general for any x, y pair. Maybe it's up here, maybe it's down here, maybe it's right here, or maybe it is this one right here. So instead of fixing it and calling it x2, y2, we'll call it just general x and y, which means that we're letting them change. So if we let the x and y change and we fix the x1, y1, and again, if it helps you for the sake of imagining, just think of this as, in quotes, think of this as like the point 1, 2. And this over here, we're going to let x and y be anything. So what would the slope between this anywhere point and this fixed point be? Well, we know that M would be y minus, let me do that in green, y minus x minus y1, change in the y, all over x minus x1. Right? That definitely tells us the slope here. This value is y minus y1. This value here is x minus x1, right? End minus start. So that's where these values are coming from. And so this will tell you the slope at any point x, y. So here's the thing. What we can do is actually solve this for y as a function of x. Right? Because we know that y is the output if x is the input. So, here's my input x, here's my output y. I can solve for this in the general form. So if we go ahead and do that, I'm going to scoot down here. M equals y minus y1 over x minus x1. So what do I do to solve for y here? Well, I've got a fraction, so I need to multiply both sides by x minus x1 over 1 to clear the denominator. So this cancels. Over here I'm left with m times x minus x1 equals y minus y1. And then again, x1, y1, you can think about this as being the point, 1, 2. They're just constant numbers. So what I'll do is add y1 to both sides to cancel these out here. And we'll be left with y equals m times x minus x1 plus y1. And this is what we call point-slope form. Another way to write this is to keep the y values on one side. I often write it like this. These are equivalent. But this is what the book uses, pretty sure. So why is this called point-slope form? Well, the last form was called slope-intercept form, right? What was slope-intercept form? Y equals b plus mx. Here's the intercept, 0b. And here's the slope, equals m, constant rate of change. So over here we have the slope. And we don't have intercept. What do we have? We have a point, any point. And that point is given by x1, y1. So it works for any points, not this special point, the y-intercept. Sometimes the y-intercept doesn't matter, or it's not physically relevant. So, and we might just be given a different data point. We want to find the line that crosses through that point. This would be the form that you would use for that. So it's got those two things you need, right? A point and the slope. So you've got everything you need. So an example of that would be something like this. 3 times x minus 2 equals y minus 4. Okay. So everything I need to know about this function is right at the surface. So we know that the slope is 3. It's given right here. And we know that a point that it passes through, x1 comma y1, is given here, 2, 4. You say, well, Mally, why are they negative and you're taking them to be positive values? Well, again, they're negative because they came from the slope formula, which is a ratio of differences. right? So that's why they have minus there. But really the point, since we're finding the difference between the x values and the y values, the point itself are just those numbers 2 and 4. So the one thing to just remember here is, since it's a difference, if you go in and you're looking at this and you see a point that's plus, then really you're still talking about a difference, right? So another example, if I had 5 times x plus 2 minus 3 equals y. Well, what do we know? We know that this is usually x minus 2, and we see an x plus 2 here. So what we can do is a little bit of a rewrite and say, well, this is really x minus negative 2. And this minus 3 over here, if we scoot it to that side and we say this is y plus 3, again, we know that this is usually a difference, so it's y minus negative 3. So we have 5 times x minus negative 2, y minus negative 3. And so again, we see the slope is 5. And then the point x1, y1 that it passes through is negative 2, negative 3. Oops. We see that sign here and here. So again, since it comes from the slope formula, we want to be thinking about these differences. Don't get too hung up on that, but just to know that this is where those come from, okay? And why you need to keep your signs straight when it comes to the formula. So just think it through. Make sure it lines up with what you know about this form, either this one or this one. Okay, so if you see a plus, think, is that really plus, or is it, does it need to be rewritten to be in this form? It's only in this form that it really represents the linear function and those what we call parameters of slope and the line. So let me give you a quick example of why this is sometimes a superior form to use instead of slope-intercept, which is, if we want to know, find a formula for the linear function, or I might even say for the line that passes through the point 1, 5 with a slope of 10. I don't know why I put that in parentheses, of 10. So if you are kind of addicted to the slope-intercept form, what you'd have to do is use y equals b plus mx. You'd have the slope, and then you'd have to plug in this point here to go solve for what b is, and that would take a lot of time. Not a lot of time, but it is less efficient, and we might not care about the vertical intercept. So since we have a point and the slope, then we've got everything that we need. So I'm going to use point slope form. Which looks like this. Y equals m times x minus x naught plus y naught. Again, either or, if it's x1, y1, or x naught, y naught, doesn't matter. You could even use a and b. That's how it's written in some places as well. But, so we know x naught, y naught is a point, is on the line. So here's my point, x naught, y naught, x minus 1 plus 5, and then my slope is 10. So here's again my 1, 5, 1, and 5, and now I'm there. Now what's nice about that is, I'm done. I see the information that I was given, right? Here's my coordinates, and here's the slope. So it's easy to see what's happening in the formula. And I can also now manipulate this if I really want y equals b plus mx form. I have options. I can do that. So what I could do is keep going to get y equals b plus mx if desired. Not always called for, right? So don't just kick in your muscle memory here, but you could say, well, let's carry out this operation here. It seems not as simple as it could be. 10x minus 10 plus 5, which then simplified gets us 10x minus 5. Well, now here's b plus mx form. I know that the y-intercept is 0, negative 5. It crosses the y-axis at negative 5, still has slope of 10. So I have a little bit more information. So depending on what form you want, you get a little bit more or different information. But regardless, you could use this to sketch a graph, even if just to get a quick sketch in your head, not to do a perfect one, but say, well, I'm at the point 1, 5, I've got a slope of 10 that's up 10 over 1. It's going to look something like this. Right, a pretty steep line. Because you might be comparing this to another line that's doing something like this, and you'd know, oh, this has a very steep increase as we go left to right, whereas the other has a very steep decrease, etc. Just kind of outlining some of the reasons why we'd care. But given any point and the slope, you can then just create the formula for the function in point slope form pretty easily. Okay, so here's an example where we might use point slope form in a physical context. So let's say we have a driverless car that's being test driven on a long straight stretch of road. So at the 10-mile mark, we know the clock read 30 minutes and the car is traveling at a constant 50 miles per hour. So we want to write a formula for the distance of the car as a linear function of time. So distance traveled as a linear function of time. So we got to mark out some stuff. You know, what do we want? We want to write a formula for the distance traveled as a linear function of time. So I'm going to call distance d. I'm going to call time t. Why this keeps happening over and over. And we're going to say this is in hours too, by the way. Distance traveled in miles. And if it's not given to you, you would need to claim what the units are. So distance in miles is a linear function of time. So what we really want is d is a function of time, and that's going to be equal to either b plus mx, or we could put it in point slope form. So let's do that. So let's do m times t minus t naught plus d naught, right? Where t naught, d naught is a data point we have. So what is t naught? This is a time distance pair. So this is really what we want. So what do we have? Well, we have some stuff. Just looking at this, and it might help to draw this out too, just so you kind of understand what's happening. Got a long stretch of road, got this perfectly drawn car, because we're all artists and we're good at this, and it's going this direction. We know it's going constant 50 miles per hour, right? That's its speed. And we know that at the half-hour mark, it had traveled 10 miles. So, you know, if this is like 0 out to here, this is 10 miles, and we know this happened at t equals 0.5. So d equals 10 miles at t equals 0.5. Notice how I'm getting my variables into the mix here. Why did I use 0.5 instead of 30? How many minutes is in a half an hour? Or how many minutes are in an hour, rather? 0.5 hours. Since we're in hours for time. So I know that t equals 0.5 corresponds with d equals 10. Hey, that is one of the things I'm looking for, is a point, a pair, t naught, d naught. So that is going to be definitely my t naught, d naught pair. And I'm also looking for, so I've got that, and I'm also looking for m, the constant rate of change, right, the slope. Do I have a constant rate of change anywhere? Right, m is my change in distance over my change in time. Does that sound like anything I've been given? Yeah, it's my speed, right? 50 miles per 1 hour. So I know that this is actually my m value. So now I've got everything that I need. So d equals f of t, which is 50 times t minus 0.5 plus d naught, which we said was 10. Try to clear that up a little bit. T minus 0.5 plus 10. My input-output pair, my rate of change. I can judge this book by its cover. I know everything I need to know about this linear function. Tell me any amount of time, and I can tell you how far that car went. So again, like we did last time, you could go and solve and put it into slope-intercept form. You might know that the vertical intercept here means the starting position along the track, right? When time equals 0, how far down did it start? That might be a good exercise for you to go check in on right now. But I want to give you one last example of how we can find the formula for a linear function if all we're given is just 2 points on the line. So I'm going to bundle this into a contextual problem too. So again, this is going to be the type of problem where you're given 2 points A, B, C, and D, and you're going to generate a linear function. So here, let's say I tutored for 2 hours. Oh, my handwriting is really hard to read here. I tutored for 2 hours. And earned $130. The next week I tutored 5 hours and earned $325. So let's assume that this is a linear function, and we're going to create a formula for earnings as a function of the tutor's hour. So we'll call earnings P for payment. As a function of hours tutored, we'll call that H. So H is my input, P is my output. So here, what do we want? We want P equals f of H to be either, B plus MH, or to be equal to M times H minus H naught plus P naught for a point that we have. So this is what we want. What do we have? Well, we have 2 data points given. 2 hours earned $130. So when H equals 2, P equals 130, which gets me a point 2, 130. And we know that when h equals 5, when I worked 5 hours, my payment was $3.25. So I've got 2 points. What do I need? Well, I need a point and the slope. So I need 1 point, h naught, p naught, and I need the slope, m. Well, I've got 2 points, so I definitely have 1 point, and it turns out it doesn't matter which I choose. So let's say, yes, okay, I've got 1 point, so I'm good. But I don't have the slope, right? My rate wasn't given. I just was given how much I earned based on how much time I put in. So I don't have that slope. So we need to find slope. And so we got to remember what that is. That's the change in y over the change in x. But here, that's the change in my payment over the change in the number of hours, which is P2 minus P1 over H2 minus H1. Dang, well that means I better have 2 points to find the slope between, and I do, right? So this is really then 325 minus 130, difference of my y values, all over 5 minus 2. And so what do we get here? 325 minus 130 should be 195 all over 3. And then we can go ahead and divide that. Turns out it is divisible by 3, and it becomes 65 over 1. You'll notice I tagged the units in there. What are the units? Units of P in dollars over the units of H in hours. So this is $65 per 1 hour. So I have my slope now. I have a point. So we are good to go. So I can go ahead and map this in. So then P equals a function of H. And that's the slope, which we said is 65 times H minus 2 plus 130. Right, so here's this guy got drawn in here, and the slope got brought in here. So I've got everything I need. I've got how steep this thing is, and I've got a point, an input-output pair, right, to 130. I know that I earned, $130 for 2 hours of work, and that my rate is $65 an hour. Another way you could go about this, again, is to use this 325. It would be the same thing. H minus 5 plus 325. These are actually equivalent, okay? So now this is where it can be confusing, because how can it be the same line if it's got different parameters, right here? Well, one way to check is to just go ahead and solve this through, and what you'll see, not solve this through, distribute and simplify. So if I distribute this through, 65 times H minus 2, right, becomes 65H minus 130 plus 130. Well, these guys cancel, and we're just left with 65H actually. And the same thing will actually happen down here. So 65 times H gives me 65H. 65 times 5 gives me negative 325. And then I add 325. What do I get? 65H. Now, it's not that the extra parts will always cancel out, but what will happen is that you will be left with the same exact formula. So these are equivalent, they're just written differently, right? So when they're simplified, they are exactly the same. So if you're given 2 points and you're not given the slope, but you need to find a linear function, you still need that slope, but since you have 2 points, you can go in and find it. So these are the different kind of variants of problems you'll see in this unit. And moving forward, of I'm given a point and a slope, or I'm given the y-intercept and the slope, or I'm just given 2 points. But usually you have to figure out, the tricky part is interpreting the statement of the problem to see what do I really have, right? Getting this column of what do I have really concretely written out, and how does it translate into what I want, that's the hard part. So it can come in different forms, so all I'm saying is just take it slow and really process what is the information that you have and how does it relate to what you want, or does it give you something that you can use to find what you want. Alright, so happy hunting, and we'll see you in the class discussion.